Welcome to CS 219 day 6, Tuesday, July 21st. So we are almost halfway to the second week. So that means that you have your midterm exam coming up a week from tomorrow. So FYI. Hope you all are doing good. So today we are going to continue where we left off. So this is a tentative schedule here, but we were just going to talk about the interrupts. We had just finished talking about the instruction fetch and execute, and I was showing and I showed you that longer example about that. And here, let's actually go here. There's cameras. Move the cameras out of the way. And we had just done the example. This one. We have talked about interrupts like in sort of a overview of the two possibilities that you could have, being one of them being whether like when you do I/O, there is some sort of pause and then you wait for the entire like I/O to happen, and the other one is you tell the I/O you want something done and then you keep going. But then eventually the I/O comes back and tells you, it interrupts you and tells you, hey, I'm done. And you're like, okay, thank you. So we have a question. Will there be a worksheet so we can get an idea of what kind of questions will be asked in the test? So the best kind of example of the questions is going to be the exercises that the TA is doing on Friday with you guys. So for example, you will get a question on Amdahl's law, like the one that you got on Friday. Or you will get a question on calculating, like not maybe I'm not gonna ask you maybe like calculate the harmonic mean, and if I did, I'd give you the formula. But either way, the test is open notes. But I would probably ask you like the advantages of one over the other kind of mean. So you're gonna get the same stuff that you get on Friday. So we'll have a review day as well. I'm not gonna ask you obscure stuff, although technically, even if I don't necessarily talk about everything, the best way to know exactly what the test on is based on the readings. So as long as you keep reading and you watch the lectures and see what I'm emphasizing, then you should be okay. So yes, it will be a good study guide to do some of those questions. I can even try and come up with a list of some questions that might be better. But that's pretty much what I tell the TA. Like I tell him, like I told him, for example, to do 3.1 on Friday, because it's another example of this stuff. Because you will get one of this in the test, and that's gonna take you like 5 or 10 minutes to do it already. So, yeah. Anyways, another example of what you're gonna get in the test is gonna be this whole interrupt thing that we're gonna do. So, let's go ahead and do that. So. Now that we kind of talked about how to do the interrupts, and then that showed you like in terms of time, how if you have 2 interrupts in a row, you have to wait for the first one to finish before the second one can go. And ideally, here in the scenario where you have a shorter sort of interrupt, you can get work done ahead of time and not really lose any time while the interrupt is happening, while the I/O is happening. And then when you get the interrupt back, it's just a very fast thing. And that's when you get the most efficiency. But when you have multiple sort of I/O operations, it's possible that you get to the second one before the first one finished, and then you're still waiting for the interrupt. Basically, the interrupt again is the I/O coming back and telling you, "Hey, I'm done." And so that's more of the real scenario. But you're still going to get a little bit of efficiency by doing this, although you are sacrificing a little bit of efficiency. On the other hand, to implement an interrupt system, compared to just flat out I/O, you pause. But that is a cost that is worth paying because of the amount of time you save by being able to not have to wait for the program to go do the I/O in its entirety. You can let it do its thing while you're continuing. So anyways, this could be something that I could ask you on a task, like between these two pictures to compare and explain what's happening. So yeah. So anyways, what the interrupt looks like in adding into your instruction cycle state diagram from this, you can see that we add an interrupt to that. So Now you have to actually think about it. So now, when should you do the interrupt? Like, do you just do it at any point in this cycle? Like, do I just like flat out, to the other one? Do I just flat out like stop right here and do that? And how do I even stop? Like, realistically speaking, when we think of the word interrupt, we think of like one of you right now, just while I'm talking, flat out just kind of jumping in the conversation, right? That would be an interrupt. But computers can't really do that, because the only reason that somebody can do that to us is because our hearing sense and our eyes are always working even when we're talking. And so they're always listening for audio. And so when we hear audio, or when we see somebody that interrupts us, we are capable of receiving that signal from them at that moment, right? Eyes and ears. I guess if they smell really bad, they could interrupt us because they come into the room and they smell like that, okay? Or, I mean, they could be bringing cake and they smell the cake. So these things are actively listening for I/O, for external stuff, right? Your body's actively listening. However, that information has to be processed by the brain, right? You have to be processing what you're seeing, what you're hearing, what you're smelling, or if somebody touches you, what you feel, right? So all that nervous system stuff. If you were able to flat out shut down one of your senses, like hearing, you could just like push a mute button, then you wouldn't be able to hear someone if they called out to you. Furthermore, the fact that you're listening to someone, somewhere in our brain that is like processes going on. Like there's processing happening inside the brain. I could argue, and this, I don't know much about biology in that sense, but I could argue that the fact that we are processing the audio that we're hearing could take away from our brain power to do whatever we were doing. So if we were talking, we could focus more on like trying to remember what we're trying to say than having that, dedicated part of our brain constantly listening in. So the same can be said to the computer. We have to have inside of an instruction cycle a part that is dedicated to actively listening to the outside world, which is in this case is to the interrupts. And us putting that in is going to take a little bit of efficiency away from just focusing strictly on running the whole fetch and execute system. And that's why every single cycle that you do, you have to dedicate a portion of it to check for interrupts. You don't have it constantly on. So you don't want to just be flat out interrupted in the middle of the internal stuff, because if you were, you would have to okay, so suppose that suppose you sent a request to main memory saying, hey, I need this address. At that point, you as a CPU or the processor have given the request and you're waiting, okay? Suppose that at that moment you were listening for an interrupt and an interrupt came. The interrupt was like, hey, I/O device is done or something. And while you're doing that, the memory gets the notification that you want a specific address, gets that request, puts it in the system bus, which we'll talk about later today, sends it into the processor, and the processor should be ready to receive that information. If you're busy with the interrupt when that comes in, that's just kind of like, imagine just as like information just splattering to a wall and crashing and disappearing because nobody received it. And so now you've lost information. So you cause more problems than you solve by having an interrupt at that point. So you can't do any of the interrupts in the middle of the cycle. Otherwise, things will break. So you do it at the end of the cycle. And at that point, you don't have any information that's sort of in the pipeline to come to the processor or to leave the processor. At that point, you're just kind of free for a second before you start the next instruction. When you're doing this thing, you either just did an operation and you're ready to go and read the next thing from memory, the next instruction. So you have sort of a moment to breathe. However, you do have information technically because you need to keep track of the program counter and you need to keep track of what's in the accumulator. The information register, you don't technically because you're about to read something into it. So it doesn't matter what you currently have there. But you do still need to keep track of that at this point in time. So if you do this interrupt check, and there is such an interrupt, it's not just a matter of just handling immediately. You are going to have to back up somewhere the program counter and the accumulator or any other registers, basically. So you still have to have a way of backing that up. And yes, there is somewhere in memory the sort of a special spot to do that, which frankly is just really just copying it over to a cache or something and then bringing it back later. But that's something that you still got to consider. You have to go to the most basic sort of operations here. You can't sort of oversight anything like that. You know, the interrupt itself has to be something that is added in, which means that every single cycle you're adding in a tiny little instruction or a tiny little operation that it does the interrupt check, and that's going to lose efficiency. But you know, people have done tests and they still agree that having that little check there every single cycle and having the ability to have interrupts outweighs the time wasted by just having things be done in a sequential manner where you can't, you know, basically delegate that IO to do its thing while you're still working. You know, looking at these things basically, you know, this versus this one being basically no interrupts, and then the left side being no interrupt and the right side being with an interrupt. You know, even in both scenarios where the IO takes a long time or a short time, in either scenario, you're still going to gain efficiency with interrupts that is worthwhile having the whole interrupt segment to the instruction cycle added. So, yes. Oh yeah, if I there's no way I can figure out here versus in Twitch I could see when my internet goes down because I can see the streaming here right on the video. Here on WebEx I have no idea. So if I go offline, you guys better start posting messages so that I know. So yeah. Anyways, at least I'm recording it, so I don't know when the thing went away. Is it more conceptual or practical? Both. I'd say more conceptual actually than practical, because the practical stuff will be like the Amdahl's law. That conceptual is going to be like talking about how cache works and why it's good and bad. You know, once we actually get to cache, but like why interrupts are good and bad, basically. So well, I'm glad it's fixed now. Next time, if the internet lags because I have no way of checking that on WebEx, you guys should go on voice chat and talk. Because typically what ends up happening with my internet here is the upload speed dies, but the download speed remains steady. Or I mean, sometimes it just fully dies, but like most of the time I had a situation where the download speed is okay and the upload dies. So I can still hear you guys. I just can't upload video, I guess. So, yes. Okay. Where would you want to not have an interrupt handling? No, you always want it, basically. That's what I'm getting to, is that it's always worth it. But I suppose in the scenario where your computer had no I/O devices, then you wouldn't necessarily need an interrupt for that sense. But even then, you could sort of extend the interrupt functionality to other things, such as sending a request to main memory. If you can do something else while you're getting that subtract from main memory, that's great. So interrupts are basically going to be always good in that sense. Now, as I was saying or teasing at the end of the last class, there is the idea of interrupt inception, basically interruptception, which is the idea of what if you get multiple interrupts at the same time? How do you handle them? Do you interrupt an interrupt for a higher priority interrupt, or when you're doing an interrupt, you tell the other interrupts to chill out and wait, and then when you finish one, you go for the other one? So in one of the situations, that's exactly what you do. You run one interrupt, and then if other interrupts arrive, you're only doing the interrupt check within here. I know this is only two little things here, but really what this ends up happening is this interrupt has its entire instruction cycle to deal with, because the interrupt itself is a program. And at the end of each of those individual cycles, you can add another interrupt check. Or you can just not add any interrupt checks in that, and then at the entire end of the whole interrupt, then before you go to the regular instruction address calculation here at the start of this, then you could do the interrupt check. So let me maybe I'll draw that to make sure that we understand what I'm saying. So we have questions. So interrupts are for what? Like, what are they important? Okay, so when you send an IO, when you write in your program in C++, C out, hello world, and line, that C out word that you're putting in, token or whatever you call it, variable, I can't variable, but it's an OS stream variable. Okay, that's what it is. And then you're putting in your stream insertion operators, stream insertion. So you're inserting to a stream. In this case, it's the OS stream, which is the terminal, the standard output terminal. Okay. In assembly, that gets converted, and this is the part I don't remember. Some of you guys can help me out. It gets converted to some sort of call to print to the screen. Okay, that printing to the terminal or screen will be considered output, and IO stands for input output, right? So that is an IO call. So it's a system call. Okay, thanks. So we got a system call. All right. Why is it system? Because the operating system is the one that really has communication, direct communication with the IO device. So when you do that, that takes an extremely long time compared to the clock cycle that you were talking about, how you can process so many things per second, right? One option is just to wait and sit there and wait, because I mean you are running your program sequentially, right? So one option in the basic sense is just to wait. Just like when you have a function call, your program stops and does the function call and comes back. You can think of that like the IO device. It's a function call. So you got to run all that code and come back. That's a long time because you got the IO device has to actually print the thing out and then come back and say print successful, which is kind of like your return statement in your functions, and then you continue, right? That's slow. That's very slow. IO devices can be extremely slow. The other option is to keep going. Your program can keep going. Basically, it says see out hello world or system call and then keeps going. The thing is, you can't just keep going unless you know that you printed this, because the next thing that you try to do that requires you to print something, how do you know that the first one ever happened? So your program needs confirmation that it happened. And if it's not waiting for that confirmation, the processor doesn't have eyes and ears. So it has no way of receiving confirmation because it's not listening for one. So the concept of interrupts is basically adding the ability for your program or your processor to have ears and eyes that alert it when the rest of the when the IO device sends the confirmation back to it. And so that ability to listen for confirmation is the interrupt. It has the ability to be interrupted and listening. And the way that works is you can think of like when the IO device finishes, it sends a little current on a cable saying 1 instead of 0, which means done. And so the processor, has that wire coming into it, and then when it's doing its cycle checks here, it checks to see if there's electricity in that wire, which means it's done, and then it can send a confirmation to the IO device saying receive, which could be in another wire, which is a little 1, and then they both kind of come to an agreement saying, okay, you heard me that I said I'm done, so I can stop saying that I'm done. All right, so that's sort of the process of an interrupt happening. And okay, this is stepping into the realm of asynchronous programming. So interrupts can be asynchronous because they're doing its own thing. So yes, I suppose you could say that in a way. So hopefully that makes sense. What was I saying? Oh yeah, I was talking about the interruptception. So with interruptception here, coming from Inception, so I'm trying to get to here, is the idea of what happens. Normally you have your, I'm going to simplify the instruction cycle state diagram. I'm just going to say there's a fetch and an execute, but we already saw there's a little bit more than that. There's instruction address calculation, instruction fetch, instruction operand decoding, operand address calculation, operand fetch, and then their data operation if there's any, and there's also the operand address calculation for storing if there's any of that stuff as well, right? So, but in the most basic sense, this is kind of how it goes, right? Fetch and execute. And so in this case, we go ahead and we kind of add the extra check now, and that's going to be your interrupt check, which if there's no interrupt, you go there. Otherwise, you go when you handle the interrupt. The interrupt meaning that there's somebody that's telling us that they're done and they want us to acknowledge that. Okay? And if there's anything additional to that to be done. Because here's the thing. So it doesn't have to be just output interrupts. There could be input interrupts. Like we request information from the terminal, you know? And those might be more critical where we actually have to wait for them to be done. But there might be other stuff that we can handle while we wait for that input in some scenarios. And some of them that we just flat out have to sit there and wait, you know. If you have a program that says like CN and then you're reading in something, you can't really do anything after that if you're actually dealing with a variable that handles CN, right? But technically, if the next line after CN has nothing to do with the variable that you read in theory, you could do that ahead of time. So yeah, that gets into some prediction stuff, but you get kind of the idea. That's funny. It's like, sorry, I interrupted. See? But that's because I have my interrupts on in my brain. Otherwise, I would just, that'd be like shutting down the chat and just going full lecture mode. So, interrupt using IDT table to jump back. I don't know. That's the I don't even know what IDT stands for. I don't remember that. That's assembly land. So I'm not sure. If you tell me what IDT stands for, maybe I'll know. But anyways, so with the interrupt, what kind of interrupts could you have? The ones that they show in the book, for example. Well, the most basic one's the one we're talking about, printing stuff to the screen. So we have something like a printing interrupt. But there can also be sort of a request for information from main memory or from the hard drive, right? The hard drive is going to be one of those that is very slow. So that can take 1 millisecond seek time. Well, I think we'll at some point in the class we will talk about hard drives and how you calculate the seek time based on the spinning speed and whatnot. So that's going to come at some point. I don't know when, but it will, because I remember that being in my own. So if not, I'll throw it in at some point. But yeah, so we have a disk interrupt service routine, a communication interrupt. Could be like receiving a signal from somewhere or even from the internet. Interrupt descriptor table. Let's see what this is. Details in the description below apply to x86. Okay, so those are the different possible interrupts that you're getting, I suppose. But that's actually more for an error. I think this interrupts is not necessarily the interrupts I'm talking about. This is actually more of like exception handling interrupts, I suppose. Because I'm seeing a lot of, like this interrupt seems to be more like error handling, This all seem to be error related. So I would not, I would say that this is not necessarily, when they're talking about interrupts here, they're talking more of like about an exception happening in the system, like an error happening, and the system stops. While this might still be using the same sort of interrupt check as the instruction state cycle, that's not the interrupts that we're talking about. So I would say no, this is something a little bit different. Okay. I don't know if this is handled also as a regular interrupt. I'd have to read about it, but just kind of looking over here, this is more for error handling than receiving information from I/O devices in the disk, because I don't see anywhere in our table talking about receiving information or sending information, except for maybe the single step interrupt, which I'm not sure what that one is, but the other ones do not seem to be the case. So I would doubt it, but I'll have to check. I'll have to read that later. So anyways, back to this. So we have this different kind of interrupts, and so they might have different priority than other ones. For example, the communications interrupt You know, that one could have the highest priority because an IO device, you know, such as like printing and reading, it can wait for you. You know, if you have information in the user typed in or something and it's coming in that you requested, or that you send something to print out, it's not extremely critical. Like if the computer is doing something else in the meantime, nothing bad is going to happen. On the other hand, something like communications, you might be receiving a signal from a device, and that signal is not something that the device can kind of just sit there and wait for you. It's like the signal is coming in whether you want it or not. And so those are like higher priority interrupts where you actually want to stop what you're doing at the next possible chance and receive the information. Something like a disk interrupt, you want higher priority than the printer stuff, but you don't want it as high as communication. The reason why you want it high is because the disk is so slow that when you finally get it, you're like, yes, please give me the information. So that is higher than something like a print, but lower than communications, where it's like time critical because you will lose the information otherwise. So in one of the ways that we can handle interrupts is sequentially, right? So if we're running a program, and the program has sequential lines of code here, and suppose that we are working on this line of code. At this point in time, let's say, you know, and each of these has their own little tiny thing here, right? This whole thing is basically, oh, hold on, don't want that kind of paste like this. Let's try that again. There we go. So you could consider each of these lines to be basically a bunch of these, okay? So this is me zooming in for the 1, 2, 3, 4, so maybe like these. Okay, so each of those is one of those lines. Okay, kind of, you get that. So when suppose that you're actually, now we're going to enhance that. So suppose that the real interrupt happens, or the signal happens right around where you're doing your fetch. Whoa, hold on, make that smaller. Okay, that works. At that point, the interrupt is just kind of lit up. You know, it's gonna. So you got per se you can think of receiving a little signal. That's when it arrived, but you're still at the fetch part of this. So then you do your, actually technically, my bad. It would be the second line because we put it as the second line, so it would actually be here. Okay, so that's when this lights up. But nothing happens then. It just gets ignored completely. Then you do this. And then finally you do the interrupt check. And that's when you see that this is waiting. So at that point, you do not go this way. What you do at that point is you actually handle it. So you go this way. Okay? At that point, you do what's called the interrupt handler, and you run that interrupt, right? So that interrupt has its own code, which has to run. And that code itself will look pretty much the same as the other one, in the sense that you have your fetch and execute. Now, within that code, you might also get another interrupt coming in. And so here's the thing. Do you have an interrupt check in the interrupt code, or do you not? In one scenario, in this scenario here, I have an interrupt check, but I could also have basically erase. I could erase these things here, like that, and then it's gonna be look at thick line, but whatever. You know, I could have something like this, in which case, if an interrupt arrives, it's just gonna get ignored until I finish this handling of the interrupt. And only when I go back here, then I go back here, and technically, I suppose there's a little error that goes back here to check for interrupts right there. So when I finish handling the interrupt, and then I check for more interrupts, and then I can handle potentially the second interrupt that arrived, right? Which would be basically the same thing here. This is a sequential way of handling interrupts, and that's what it's shown in figure 313. So that would be this right here. So that's basically what I drew. The problem with this, again, is that it's not giving priority to any interrupt, and an interrupt itself can take a while. And if while that is happening, you receive a higher priority one, like I said, like a communication one, that information is going to get lost forever. So what you need to do is your interruptception, in the sense that the interrupts should have an interrupt check within their own sort of instruction cycles, which is actually how I had it in the beginning. So let me go ahead and just actually copy this whole thing over. So in that version, we are going to actually just each of the instruction cycles of the interrupt code will have a interrupt check within its own. By doing this, if another interrupt arrives that is higher priority, such as a communication interrupt, then this will actually get interrupted itself. So actually, suppose it arrives like on the third line. So this whole thing is a zoom in of like this line, and this line. Okay, so it's and maybe this one. So it's arriving on again on the second one. Okay, so that one right there. So I suppose again, you can think of this as like the wire coming in and lighting up, and then if this thing was like here in this case, then it's gonna get here, and then it's gonna see it, and it's gonna handle that. If it's higher priority. Here's the thing though, technically that wire is not gonna come to both there and there as well. That way, if it's lower priority, then this thing just ignores it, but then when it gets out of this, it'll handle it. Because it's possible that this is like the interrupt that just arrived is super low priority, and we're already deep into like an interrupt inception kind of thing here. But in this case though, we said it's high priority. So what happens there is this whole thing gets interrupted, and we have that higher priority interrupt happen here. So we have to shrink that so it fits. So this gets interrupted right there. And from there you could say another interrupt arrives. But that interrupt that arrived is not as high priority. It's higher, it's lower than the current one that we're at, but higher than the first one. And in that case, this interrupt will finish first. So it'll run all this code. And when it comes back here, maybe the one that arrived is higher priority than this one, so it'll stop again and run the other interrupt. So it matters basically what the priority of the interrupt is. So looking at the book's figures, you can see here that in this case, we got sequential interrupts, so we got do one of them and then the other one. But in this one, in the middle of this interrupt, we'd run another interrupt. And an example of priority for that could be this sort of time sequence. So we start at time 0 and we end at time, let's say 50, okay? So we're running from 0, and then we get to time 10, and then we get a printer interrupt. So we stop the main program and we handle this interrupt. How is priority established? You can say that's hard-coded in based on the type of interrupt that you get. So we always say that this interrupts have higher priority over this and that. So it's probably some variable that's kept in there that's flagged or something. So yeah, so you start running this and you get to time 10, and then you go ahead and you run the printer interrupt. And then at the middle of this one, so that's about 15, 5 seconds into this interrupt, time 15, you get a higher priority communication interrupt. So at that point, this stops and it runs this interrupt. Let's say that at time 20 here, right in the middle, you get a disk service interrupt. However, you don't do anything with it. You acknowledge that you received it though. So it's there because you're still checking for those interrupts, but it's lower priority, so you don't deal with it. You finish this interrupt, and then you go back here. The first thing you're gonna do is you're gonna check if you have any pending interrupts, and you check them, and you have one. You have a disk interrupt service. However, that one is the disk interrupt is higher priority than the printer interrupt. So while as it didn't stop this interrupt from happening, it will stop this one. So it'll actually go right in here and complete this one. Suppose that you were in here and you receive another printer interrupt. Okay? In that case, you would ignore it because it's low priority. You keep going here, and eventually you finish this interrupt, and you go back to this printer interrupt. In this one, you got an interrupt, but it's, you know, same priority or lower, so you just keep going. So you finish this, and then if you had the other printer interrupt, then you would do it in this case. So it matters the priority of the interrupt, okay? And then you can basically, once you have no interrupts left, then you can keep going on your program. Which type of interrupt is more used? Depends on what you're coding. I mean, are you coding something that is communication heavy? Then you're gonna get a lot of communication interrupts. Are you coding something where you have to access something from the hard drive, like you're watching a movie or something? It's gonna be hard drive interrupts. Are you printing just an interactive program, you know, that prints a lot of stuff out of the screen? Then it's gonna be higher priority with printer interrupts. So really, it's not necessarily about which one is more used versus which one you're using more, because more than likely these interrupts are coming because you requested them in your program. Your program probably did some disk reading or writing, it probably did some communication, and it probably was doing some printing. That's why these are being made. These are not just coming out of nowhere. You literally ask for them, basically, you know. You either, and it doesn't have to be necessarily that like you're printing stuff. You're gonna request it, you know, a signal from somewhere, and so you have to be listening for these communication interrupts, you know. So yeah, is accessing main memory an interrupt? You can handle it that way, yes. So that's the other thing that was in the book that I wanted to bring up, especially when you go back and talk about this thing. You know, we have addresses here, right? These addresses that you're working with are main memory addresses, but they can also be how you call it an I/O device. You just refer to the I/O device with a specific address, and you know, some addresses may represent main memory, other addresses may represent an I/O device. And so you would send an you would have an opcode and address, and that address is an I/O device, and the opcode might be like write to this address, which write to this I/O device essentially is going to be what's going to happen. And so you can consider writing to main memory, writing to an I/O device, or doing just about anything could be considered a potential interrupt because it's slow. Even writing to main memory can be considered slow. So you could consider all of these to be sort of interrupts that need to be acknowledged that happen. That way you don't lose information. So yeah, sure. Okay. So that pretty much concludes the interrupt talk. Again, the purpose of doing these interrupts is so that you can basically kind of like multitask in a way, because you're delegating stuff, but you're not waiting for them to finish. You know, you're like an impatient person. You want to keep working as much as you can without actually requiring something from somewhere else. And yeah, I mean, it's very useful. As you can see, it always makes things, in a sense, faster. So yeah, okay. So now, what else was there? Let's see. Open book again. You got your interrupt service routine, interconnection structures. So 3.3 and 3.4 are talking about the bus. So let's see if there's any nice pictures for the bus. Yeah, that one's good. Although, let's see if there's anything in the PowerPoint one, because they never pull up the PowerPoint one. Which one is that? This one. Okay. This is actually nice. Yeah, okay. So there's two sort of main ways of doing your communication between devices, right? So we need to do communication, right? Because I mean, this interrupts even require communication, right? I kept saying this example of little wires, but like, what's the reality of things? Okay, so if you go back to chapter 1, we kind of said that the way we link things together, different parts of the computer, are with a system bus. And the system bus is a glorified cable that's running between these different devices, right? So how do you actually communicate between them? How do you actually wire the thing together? And so there's sort of two main ways. And I'm actually going to switch to the drawing because I remember I wanted to do a picture for this. So think about like von Neumanns and whatnot. You know, you can think of this as your CPU, and you got your RAM, DRAM, and then you have an I/O device like a monitor, and then maybe you have I don't know. That's a terrible picture. I was meant to be an antenna. There we go. Okay, like your communication device or internet or something. Okay, and so, oh, and I suppose you want to have also a hard drive. So how do you connect them? One way, and because there's going to be two ways, I'm going to copy and paste my picture. One way to communicate them is to kind of have a shared sort of cabling system. So you could just have a wire that runs through all of these, and then it kind of unites, you know, together and then runs here. That it has advantages. One, it allows you to communicate everything together. So that can communicate like that. You can also communicate like this. You can also communicate if for some reason there was communication that required to go this way. I suppose they could. But the point is that anything can communicate to any direction, okay? This is great because there's only a less amount of wires running around, but this also causes some challenges. Suppose that you are getting, you know, you're requesting from main memory, you know, a specific address, okay? The CPU is like, you know, yo, give me this address, you know, and then it sends it in the wire, and it's going in there, you know, it's a merry way. It gets here. This guy is like, yeah, I'll get it, and then eventually it's gonna send it back to there, okay? But in the meantime, you know, you go ahead, and let's suppose that here there was also a keyboard. You know, you splash some keys, you smash your keyboard, and then now that's sending a signal. And so that signal is coming at the same time that you got the signal coming back from the DRAM. And so you get back to the CPU basically garbage, because you have both signals that kind of came together, you know, and maybe one signal had that bit sequence and the other one had this bit sequence. And so what ends up happening, do I have the right number of digits here? Yeah, is that you're basically what's gonna happen if some wire had no signal in one of the from the DRAM, but from the I/O device here, it had a signal with the electricity. Then it's just going to turn into one. So you kind of do basically an OR statement between them, and so you end up with just ones wherever there was a one in either of these cases, which was ones. So basically you're taking this one, this one, this one, and those are the same, and then those are the same. So 1, 1, 1, 1, 0, 1. Okay, and so that is garbage because it's neither one thing or the other, right? So this causes problems, right? So if you're going to use a system where everything is sharing the same line, you need to organize things so that they don't override each other. You have to sort of put a traffic cop so that it only allows flow for one person at a time, or one device at a time, one module at a time. Okay, so this is basically kind of like your shared system bus, and was pretty much the norm to use for the longest time ever. But eventually people kind of, you know, realize that there is a limitation to this, because what ends up happening is your traffic cop takes time as well to figure things out. So the way it works now is you basically, let's say that you want to read something from CPU. The CPU is going to be like, CPU is going to be saying system bus, I need to use a line to DRAM, okay? And so the system bus has to have its own sort of control and basically, you know, stops communication from happening in the system bus by not allowing anybody else to take over. Okay, and the way that happens is all of these guys have a light. You know, you could think of that like that way, and they all become red. And then finally, after there's confirmation that they became red, now we can go ahead and send a signal in. Similarly, suppose that the I/O device gets a signal that he wants to send to the CPU. First of all, it has to send a request to the control, and the control is going to be actually in the CPU, because I remember the control units are handled there. So it has to send a request to the control unit saying, I would like to send something in the system bus. So that signal has to go here. He has to acknowledge that such a request happened, and there can be multiple requests, so he's only going to acknowledge the first one that comes. And then at that point, he has to tell everybody, like basically make sure everybody says red. And at that time, he's like, okay, proceed, you know? And so then it sends a signal back to the I/O device saying, like, proceed and start sending. And so it starts sending the signal. And when it's done, it basically sends a flag saying this is the end of this. And then when this gets the end, then this goes ahead and sort of frees the thing. So now it's like, okay, it's good again. So now, suppose that somebody else wants to send something in, this one. At that point, he's going to send a request. Now, suppose that this was still happening. Because it's still happening, you know, then it's not going to, the request here is going to be sort of buffered, but it's not going to acknowledge it. And until this acknowledges it, then this guy's just going to be waiting. At that time, you know, this one might be like, okay, I'm done with this request. So now I can be like, okay, proceed comm device. And so it has to send the signal here. Then it's like, okay, cool. And then it starts sending it, okay? So the inefficiency here is the request handling part. Because once you're sending the information, everything is great. But actually requesting to send the information, that's when things get slowed down. So the bus is basically a traffic director. It's both the road and the traffic. Because technically the traffic director itself is inside of the control unit of the CPU. You know, there's a section of it that handles the management. But yes, the bus itself has traffic lights in a way. So the system bus works on a first come first served basis. One of the ways is to do this, yes. However, it's possible that you might have a list of requests to do that. So if nobody has a request, then yes, first come first serve. But suppose that you're handling the I/O device from here, and you get a request from the disk, and you get a request from the COM. You get them both while you're handling this guy. It's possible that that because you have two of them, you can pick the one that's higher priority. So you might be like, I'm gonna get the COM stuff first. So it's possible that it doesn't come in the first come first serve, and you get priority to one of them over the other one, because you have a choice of acknowledging who gets first. If you want to go on a first come first serve, you will let the disk drive go first. But you might be like, oh, if I don't get the COM now, I'm going to lose information there. So this kind of shares a little bit with the interrupt handling and the same idea of priorities. What you can't really do is, if you get a COM device and you're still receiving stuff from this guy, you can't just be like, yeah, send me your stuff too, because then they're going to crash. You know, like information crash, I suppose, garbled together. You could, in theory, send a request here saying like, hey, can you chill and stop sending information, because I got to get the COM stuff. But that request is going to take time, and then he has to actually be like, oh, okay, and then actually stop sending information, you know. So that could happen in theory. You could do that, you know. So like this guy just doesn't completely take over and you just send information for like 10 hours. You can do that as well. But that is going to take some time for you to send a request, and then at some point it's going to be like acknowledge, and then along with the blob of information, it's going to be like an acknowledgement to take a pause so that he can get stuff from here. So you can have interrupts as well there. So yes, the picture kind of got a little bit exaggerated. But yeah, the CPU is going to be the cop per se, you know. And he can get pretty aggressive, so be careful. So I suppose one of the things that I should mention, even it's in the book, is the idea of the bus width. And that is, what if you have, you know, how many bytes are we sending here? We were sending 2, 4, 6. So we had a 6-bit sort of instruction width, right? That we were sending. That's what information the DRAM was sending or the I/O device was sending, right? If we want to send this in one go, how many physical wires do we need to do this? That's a question for you guys. So if I'm trying to send this 0, 1, 0, 1, 0, 1, or I'm trying to send it 1, 0, 1, 1, 0, 1, I just noticed that I made like palindromes. That's cool. I didn't intend to do that, but it just did. But yeah, so how many wires would I physically need between device 1 and device 2 to be able to send this in one go? Either one of these. Not both at the same time, just one of them. 6. Yeah, 6 wires. Literally 6 wires. I need 6 wires here. There we go, 6 wires. Because that way I can send it all in one go. You know, I could put 0 here, 1 here, 0, 1, 0, 1. Or in the other case, I could put 1, 0, 1, 1, 0, 1. Okay? If I had 3 wires, so if I only had 3 wires, hard times, you know, can't afford 6 wires, then how could I send that? Well, I could send it in 2 goes, right? Like first send in 0, 1, 0, and then after that send in 1, 0, 1. However, that's going to take twice the amount of time to send the same information, right? So bus width happens to be usually the biggest bottleneck in a computer these days. Especially that's why we changed from this whole system, because not only do we have this whole traffic cop situation going on, but just like in real traffic, the number of lines, you could think of that as the bus width. And if you're trying to send in from here 10 words, which you could think of that as 10 lines, you know, and your width here is the width of 1 word, which is pretty normal, it's going to take 10 of the transmission times to send. So and how fast can you send information? Well, here's the thing. Again, so we don't go into that nasty picture. If you just have 2 devices, and suppose that we're doing the 2 parts. Okay, so we're sending 2 of these things. We have to send one of them, and we actually have to like feed electricity for a certain amount of time until this arrives. So we can't just use the clock cycle for this, because it might take more than 1 clock tick to actually send the information across the wire. Go back to the example that we did like early on in the class with electricity speed, right? We actually need to do one of 2 things here. We could be like, okay, what's the worst case scenario, the time it takes for me to transmit this? You know, if we know it takes like 10 cycles in the clock, 10 ticks, then I could maybe put it up for 15 ticks in there, and then put like a 5 tick pause, and then put another 15 tick for the second set of information, you know? So I could put this for 15 ticks, then 5 ticks of just zeros, and then 5 ticks again. I could do something like that. Or better yet, as I kind of said already, I can put 15 ticks of this, 1 tick of all zeros, so it signifies that we're going to send the next one in, and then put the second one in for 15 ticks, you know? But that's kind of hard coding the amount of time, you know? Otherwise, I don't actually need to do that. I can just send the information for 1 tick by saying that, then 0, and then 0, 1, 0, and I can still flow basically the as much information as possible in 1 tick, and the only real delay I'm gonna get is for this initial piece of information to arrive. So I can fill my highway with a bunch of information. So let's suppose that I have to send the following. Oh, well, no, not zeros, because that's what we're using as a flag. We're sending all of that in through this, okay? And we have only 3 bits at a time to send it. So what we're gonna do is we're gonna throw in here, in the first clock tick, we're gonna put in 1, 1, 1. The second clock tick, we're gonna put 0, 0, 0. We took care of that. The next clock tick, we're gonna put 0, 1, 0. Then we're gonna put 0, 0, 0. Then we're gonna put 1, 0, 1. Then we're gonna put 0, 0, 0. And then 0, 1, 1. And so on. And I guess the last one's 0, okay? We can do something like that. Or we can actually just flat out eliminate the zeros and just send in the valid information. However, if you do it like that, it's only going to work if you have if you're synchronized with your CPU. Because otherwise, if you're not synchronized, you might miss some of these things. Like you might not be reading in half this way here to here when you're switching these to 0. So if you have sort of asynchronous information, then you're gonna need to have the zeros. If you have actually managed to do the synchronous stuff, then you can keep those because you have the clock kind of lined up between the different devices. So it really depends. So I'm not 100% sure on what they use nowadays, because they kind of moved away from the shared bus, but they still have to figure out a way to kind of separate the information. So I'm not sure what the latest technology handles it, if they can do it without the zeros or not. But either way, this could all be sent in one go if we had a really thick bus that basically was like 1 1 0 1 0 1 0 1 0 1 1 0. If we could do all of that, then we could send it all in one go. Rush hour on a computer is a real thing, actually. Yeah. Is that also why there is multiple bus architecture to help with the bottleneck? Yes. When computing goes slow because the CPU is fixing a bus mess. It would, in a way. If everybody's trying to communicate, it would slow down. But I mean, these are like nanosecond slowings down kind of things, you know. You have to have like a real mess to actually slow down, like you actually see a physical slowdown. But again, we're trying to really push in the ideal world, the CPU always has something to do, and whether it's receiving information. If the CPU is working, even if there's a mess in the bus, that's okay, because the CPU is always working. What you don't want is, because of the mess in the bus, the CPU has lag time where it's just waiting to see what's coming next, because these guys are trying to figure out who's supposed to go first. You know, that's what you don't want, ideally. So anyways, this bus width is typically the bottleneck in a computer, to the point that they've been widening it. But in addition to that, instead of having the mess, let me show you the alternative. So what happened to the second picture? I know I had two pictures of the same thing. Oh, it's like mixed in here. Oh crap. Let's just try to extract it from here. Okay, and then this is not part of it. And then this is not part of it. Okay, so the alternative way of wiring this together is to have direct signals between the devices. So we could have a signal there. You could have a signal to that. Have a signal here. Signal there. And then you could also have signals in between these guys. So you could have a wire there. You might want, I don't know if there's going to be a lot of communication between the DRAM and the COM, so maybe we won't have a wire there. But, you know, I think that would be pretty much what we would need. That there wouldn't be anything else that you really need to connect together. Like, I don't see anything communication going on between those two. I don't see communication really happening between those two. I do see communication happening between DRAM and the disk. If you have a seek thing where you're seeking for information that's not in DRAM, so I could see that being a thing. But yeah, so in this sort of scenario, this is the alternative way of doing things, where you basically just throw more wires at the solution, at the problem, to see if it solves it. Basically build more roads. You know, instead of having one central road that kind of leads everywhere but is shared, then you have individual roads. And you don't have to mutually do exclusive like this method versus this method. You can do both. You can still have, you know, one additional line. We could do a different color. That is your shared system. So you can still have the whole shared situation going on here. Is that all of them hooked together? Yeah, I think so. So you could have both going on. The advantage here is that by having a direct line, in addition to having having your carpool lane per se or whatever, is that you don't have to have this whole can I send information request and then like approval or denial. You don't have to have a semaphore. You know, in this case, when you have your sort of exclusive line between the disk drive and the CPU, that would be this line here, you can just throw information there as it comes. And then here, all that's going to happen is a little light's going to check saying, you know, you got mail kind of thing. And then it's just going to wait for it to actually to be ready to receive the information. At which point that, you know, ideally what you want to do here is have a tiny little buffer where it already sends some of the information, and it's just kind of like waiting. That way, when you start processing this, then they can send the remainder of the stuff. Alternatively, you can merely just say you got mail, and it's just ready to send. So you can be working on multiple things at once, and also you can speed up the whole clearing the bus to send information over kind of thing. So that's an alternative, and I mean that works in real life too. You add more highways basically between different parts, so you don't have to go to like downtown LA. You can take a different freeway. Okay, no more. I don't see any more questions. So that's your system bus. Now, if we want to see the notes here, let's see if there's anything. Oh, yeah, there's technically two buses, right? There's one for data, and then there's one for all the requests you're making, because the requests kind of have to also be handled in a nice way. So like the request, like, hey, can I write stuff in the bus? Those have their own lines, and then the data ones have their own lines. So here you can see kind of the difference of that. Timing the signals indicate the validity of data. So that's the timing that I was talking about, the clocks. Because of the data and address lines are shared by all components, there must be a means of controlling the use. So that's what I was talking about with the traffic stuff. And what else do we need to say from this? I think pretty much we covered everything. For the data bus, that's going to be the number of lines. Again, it's going to be how much bits you can send. And again, that is called the width. And it's a key factor in determining system performance overall. So yeah, we pretty much got most of that in there. Yeah, I think there was something I wanted to say about this stuff. Let me see if it was in the book. Yeah, so see the first left cube, the square there, it says the principal reason for a change was the electrical constraints encountered with increasing the frequency of the wide buses. So, being able to communicate synchronously using the other system with the shared can really increase electricity, unless you're doing the whole thing with the little flag of zeros. And so it just becomes very difficult if you're trying to synchronize all these devices, if you have a really high clock rate. And so, you can't switch to the iPad here. You can't do the thing where you're just sending things in the clock cycles and you're using those to send information. Like that becomes very hard to synchronize. So the alternative is you just lose lose one cycle each by having your own little cycles with the synchronous stuff by doing the zero thing I was showing you, right? That's the alternative, but that of course you're losing basically half the power because we're using one for data and one to separate. One for data, one to separate. That's one solution, but of course you're basically half the amount of information you can transfer. The other alternative is just to use the clock rate of the built-in clock. But because of the distances of the cables and if you're going so fast, that's very hard to synchronize, right? So that is one of also the reasons, in addition to it being an overcrowded bus lane, that you did point-to-point, which is what they mean by having independent connections between each of the devices separately, in addition to possibly having a shared one still. So anyways, that's kind of what they're talking about with that. QuickPad interconnect, that I think was the first time they introduced the direct pairwise connection between different stuff, like different modules. And that was introduced in 2008 by Intel. So yeah, you can read more about like the actual implementation that they did in 3.5. Although does that say here? Yeah, that actually does say here. There's the bullet points are discussed in the book, but they also switched to the idea of packets, which is if you're aware with like how the internet works, they're using more packets to send information. And there is error control codes. We will come back to this when we talk about like Huffman's code and all those error handling complements and whatnot. So we will come back to the idea of how to check for code, how to check for errors in transmissions of packets. But they use packets for sending information. And there is a lot of layering going on, but I'll let you read about that on your own time. There's transmission and reception lanes as well. Because that way you can, because right now you have one lane. Because here's the thing, if you see what I drew here, there is a little bit of a bottleneck still here. The line between the CPU and the disk drive, if we only have one line for both directions, What happens if the CPU is trying to write at the same time as the hard drive? You know, they're both like, yeah, by the way, do this. And this guy's like, here's your information requested. And then you got garbled stuff, right? So you still have to request usage of this a little bit. So what they end up doing, and I suppose it would have been nicer to draw, is you actually have two lanes, just like you have highways. You know, you have a highway on one direction, on two directions. You know, two-way road, and so what do they call it, a two-lane highway. And so you have one for sending and one for receiving, transmission and receiving lines, and that's going to be your best bet. That way you can always have information flow there without requesting for access first, right? Otherwise, it'd be like we have a bridge. You know, like this, but they do this in the UK. There's a tiny little piece of road that is only one lane, and they have lights, and so the light turns on, then you can go to that piece, and if the light turns off, then you can't. And so they basically let traffic flow that way, and they do that I think when they're fixing roads, or again if there's like a bridge or something that's really old, and you know there's only one car that fits, they do that. So that was kind of cool when I went there and saw that. You know, I was driving stick shift on UK, which makes it extra hard because it's on the different hand. You shift with a different hand. Like it's actually this way. Yeah, you shift this way. Anyways, PCI. I'm not gonna really talk much about it, but ultimately, it's sort of a high bandwidth bus of its own. So it has its own set of lanes that run to the CPU to enable it to have added modularity. So that's where you typically plug in a sound card or a GPU, and it has to have its own sort of communication system to be able to communicate with the CPU. And you ideally want it to be on its own bus. So it's its own exclusive highway just to get to the PCI. It's not shared with anybody else. That's important because when you got something like a GPU that's doing tons of information, you need to be able to communicate with the CPU. And so you don't want to have to go into the mess of the highway system to be able to do that. And that's why it's called PCI Express. However, the ongoing high demand of PCI has basically made it to the point where it's old. And so they added the PCIe, which is a faster implementation of that. So yeah, there we go. PCI, which is point-to-point interconnection scheme in the sense, because I suppose, yeah, I might be misleading in that. The PCI Express, the PCIe, that's the one that has the exclusive lanes. The original PCI was in the mix of the I think of the original shared scheme of PCI. Yeah. So normal old school PCI, which I don't think any of us ever had, was shared into the mess, which isn't really work out for something like a graphics card. So they moved it into its own thing. So they mentioned here that Gigabit Ethernet uses that, but I would not. I would say that that's nowadays they have their own little thing. Did somebody say something? I heard like a voice. By the way, nobody has said anything today or yesterday. You guys are super quiet. I'm hoping like the audio still works. PCI Express is basically a digital freeway. It's more of like your own VIP freeway between PCI Express and the CPU. So whatever you plug in has its own private road. No, the diamond lane is like carpool lane, so that's shared. You don't want to think of carpool in terms of shared stuff. So yeah, the UK has the right and left backwards indeed. So anyways, that's all I'll say about PCI. I suppose they do say that one of the biggest things is it needs to support real-time stuff, which is why they need all this flow of information. But do go ahead and read that on your own. I did briefly read it as well, but that's all I really wanted to say, because might as well move on into chapter 4, where it's I'd say 4.1 is a very important thing that you should get. Make sure when you read it, or actually you should have read it technically already, that you really understand that. So let's go ahead. And it's your own private elevator. Yeah, like think about like a VIP elevator in a high-rise building. So yeah, let's move on to chapter 4. After all, we do have tons of things to cover. So locality of reference, okay? That is going to be something very, very important that I'm going to do my best here to make sure that you guys understand between spatial and temporal, okay? So Locality of reference. Now, right now, in the way that the book is written, they don't really explain much about why this is so important. They just kind of say that they're going to talk about later, and they do when they talk about caching and branch prediction and those kind of things. This is how those things can really be achieved successfully. Because let me give you the most important. Well, let me start by introducing to you how we came up with the idea, and then explaining to you how we can use it. So, when you're writing a piece of program, think back to your 202 days, because I think all of you had to take in 202, and you probably have to write a program that, or actually 302 would be ideal. Think of 302 when you do sorting, okay? But if you did 202, then maybe you did a sorting program at some point, okay? And if not, then you were working on something like a linked list, but before that, you were doing dynamically allocated arrays, right? So, you probably had to process some information in one of your assignments, okay? So, would you agree with me that most of the time when you're processing code, you're dealing with the same variables for a repeated amount of time? And that's because you're probably working through an array, a linked list potentially, although that is going to mess with us a little bit here, but a linked list or anything else. You're working with a small number of your data, okay? And then you finish with that data, and then you move on to working on some other data. If you're doing sorting, then you're just dealing with just a potentially big, but still a piece of data. And even within sorting, if you know quicksort, for example, with quicksort, you're dealing with a subset of that. You're dealing with a partition of the data, and you're moving that around the pivot, right? You're dealing with merge sort. You're merging two pieces of the data set together, right? But you're still dealing with a small group of data at a time. If you're doing bubble sort, you're still dealing with data that's near each other. And the thing is sliding ahead, right? That's the sliding window with bubble sort. So pretty much when you're dealing in programs with data, you tend to deal with data that is around each other. Okay, that's like the neighbor data. You don't just go and pick around everywhere. The exception to this being a little bit linked list, because when you're dealing with a linked list, that could be stored anywhere in memory. So when you're dereferencing the next pointer, that could be anywhere else. But that's kind of the exception to the rule. Does that make sense? Like that when you're working with data, that you tend to deal with data that is clustered together. You're dealing with a specific set of data. Okay, good. So if we were to kind of graph, and this is what the book tries to do, how you deal with the data, I would say that if I am dealing with data here in my program, I'm going to be dealing with the data that's around it. And then at some point, I'm going to start dealing with the next section of my data. And that is also going to be sort of a bunch of data. So if you think of quicksort, this could be one partition that you're dealing with, and this could be another partition that you're dealing with, like the left side partition and then the right partition, right? So it's sort of important to know this, because you can use this information to sort of predict the next data that you're going to be dealing with. So if you're working with data here, odds are that you're going to be dealing with the data that is around it pretty soon. Okay, that's the side of data. Let's talk about the side of instructions. When you're writing code, it's sequential code. You work from top to bottom, right? Suppose that you did not use a single if statement or a loop. You just went for flat out code, just like you're scripting or something. I don't know. Say you're right here. Because you're going from top to bottom, there's like 100% chance that the next instruction is going to be this, because you don't have any sort of jumping statements, okay? However, suppose that you did have if statements, loops, and that kind of thing. There's a very high chance that still the next line of code is going to be this. Not 100% anymore, but maybe like 90%. The other 10% means that this instruction that you just did was maybe an if statement. And if it was an if statement, then maybe the else clause is down here and the if clause is here. So yes, while you could go here, I would say 50-50, that you could also go to the else clause. Alternatively, if you're doing a loop, you might be going code, 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 and then you're like, well, 90% chance here, except let's say that this is where the loop loops around. So you're really only running this code, and you're running this code maybe 20 times, and then eventually you're going to get out, and then you're going to run this, right? So I suppose you know, as you're running this, you'd be like, there's a very high chance that this will be the next line, but then you keep going up here. Eventually, you figure out that after this, the next line is probably going to be this one. Regardless of that, that's your branch prediction, which we'll get to. But regardless of that, even if you can't really be, I was going to say you can't be that smart, but I don't really think I'm talking about you. I'm talking about a computer. The computer can't be that smart to maybe figure that out yet until we introduce branch prediction. You can go ahead and say that it's still a very high chance that the code that you're working with, you know, around that is going to be the next code that you're dealing with. Even if you do loop around, you're looping around for these many instructions. You're not looping to the top of the program potentially. So yet again, you know, the code around your code has a higher chance of being the next thing that you work with. Okay? So this sort of spatial relationship between the data being around each other, or the code being the surrounding code, is called spatial reference. Reference or locality of reference? Shoot. Spatial locality, yeah. Spatial locality. Okay? There's also temporal locality. That's like the stock market. Or at least what people hope the stock market would be like. Which is previous, you know, the disclaimer that they give you when you try to invest. They say previous performance is not a signal of future performance, right? So, you know, most of the sort of machine learning in general, by the way, works in that sense that you're using the past to predict the future. That's what machine learning boils down to. You're not trying to do magic here. You're just trying to say, historically this has happened, so I expect this to happen in the future. Okay? If a trend doesn't follow that, your machine learning will fail, you know, without a doubt. So, similarly here, temporal locality refers to the idea that if I ran an instruction already, there's a high chance that I'm going to be running that instruction in the future. Why would that be the case? If I'm in the loop. You know, if I'm in the loop and I'm running these set of instructions, there's a high chance that I'm still going to run them again because I'm still in the loop. And even if I'm in sequential code, you know, there's still a chance that the instructions that are going to happen, that just happened, could happen again if I was to hit a loop at any point in time. So it might be useful to keep track of them. Okay? So ultimately, spatial and temporal localities are useful to sort of predict what is going to come next in terms of instructions or data. And that's going to be very, very useful for us when we try to make things more efficient by having things ready to go. Now, the example that the book gives with this is somebody working in an office, and they say, I don't have here this. So I got here some papers, right? Imagine each of these are files. So I go to a file cabinet, and I'm working on a debt collection. Okay, so I got a bunch of debts that I gotta look at every day, and so I go in there, and imagine that I just went ahead and picked up one paper. Okay, so I go back to my desk and I work on this paper, and now I'm finished. Now I got to go back to the next room, to the file cabinet, to get the next paper in line, okay? So instead, I'm lazy. What do? I grab a stack of them, and I take them to my desk, right? Because I'm going in order, then I can start, you know, I can work to the stack, finish the stack, take the stack back, and then take the next stack. That enables me to have to go to the file cabinet as long. However, how much can I really have in my desk? Could I just bring the entire file cabinet? That would be the ideal scenario. If I could just have the file cabinet next to me, because I could work to them faster and I don't have to do exercise. However, I am limited by the amount that I can carry in my hand, because, you know, paper can get pretty heavy, and maybe my desk is certain size. So I can only carry a stack that's maybe like this high in reality. Okay, so I'm carrying the maximum stack, and I put it on my desk, and I work with that. But now here's the thing. Suppose that this debt collection stuff, you know, it references another debt. So if it references another person's debt, I got to go handle that as well. So in that case, you know, I might not have that in this stack. So while I try to predict the next thing that I got to work with by grabbing a stack kind of a little bit before and a little bit after, that would be sort of my spatial locality. It's not going to help me much if, like, as I'm dealing with something in the future, it references something that I looked at already, and I'm going to put that back already. So what I have to do in the file cabinet, it might be good if instead of just grabbing things, you know, in bunches, I keep some of the stuff that I already did with me, the latest one, and keep it here while I'm doing new stuff, in the case that it references the old stuff that I work with. That's going to be sort of your temporal locality, okay? So that's locality of reference for you in simplest terms. It's the idea that when you're working on something, there's a high chance that the data that you're working with is going to be bunched up together in memory, so you can have, be able to take advantage of that for sort of chunking more, so you don't have to keep communicating with memory. And also, in terms of more of the instruction side, but could be for data as well, if you use something already, you're going to use it again. And this is true if you're dealing with even with sorting. If you're sorting a partition and you have to pull up a specific index, you might have to move that again pretty soon if you're working on sort for that. You're not gonna have to pull data that is completely unrelated to the array that you're sorting. You're probably gonna have to pull data back from the same array. So given enough times that you're doing this, the computer's gonna be like, hey, this guy's really working with this array. It might be useful to keep this accessible somewhere in like the cache. So that's kind of gonna be the main purpose of this. Now, why is that important as a programmer? Because while the computers are really smart nowadays to be able to predict sort of our usage, we should try to make it easier on them to predict that. When we're using something like a linked list, it's very hard for a computer to predict what's going to happen next, because your linked list kind of point to anywhere in memory. However, if you're running this processing on the same linked list a couple of times, it's going to be starting to remember that you're using these specific spots in memory, even if they're in completely random places. That will be your temporal locality. So temporal locality, a linked list can be handled if it sees that you keep accessing the same spots in memory, which happen to be your linked list. However, spatial locality is going to be defeated with the linked list, because just because somewhere in memory there is a specific index of a specific part of the linked list, it might not mean that anything around that is sort of related. So they're not; these things are not necessarily like they don't necessarily have to help each other. They can be mutually exclusive in the sense that sometimes a program might have high spatial locality and no temporal locality, such as the sequential code. If code is sequential and you run one instruction only one time and never run it again, there's no temporal locality, because what you just did will never be used again. However, if your code is literally just a big loop, then there's going to be absolutely everything temporal locality, because you're always repeating the same instructions. And I'd say that the majority of the times that we write code, we have loops in there, or functions. Functions is the same thing. The pieces of code that a function runs, when you call the function again, you're going to be using those same instructions. So yet again, that will be something that you can remember as temporal locality. If you use a function, there's a very high chance that you're going to use a function again. If you use a piece of code that has a loop, there's a high chance that we're going to loop again. So we want to keep that accessible to make it faster. If we use data, then we're going to probably use that same data again. Again, that's temporal locality. Spatial locality is, if we use data, odds are that the data that's near that is going to be used in the future, so we should grab it as well. So the biggest thing is a lot of people seem to always get these mixed up together, so that's why I keep trying to repeat the same thing over and over again to hopefully for you guys to make it easier to remember. So again, spatial locality has nothing to do with what has been done in the past or the future. It's just saying, if we're using data, we're going to use instruction. We're going to use the data that surrounds that data in the future, possibly. Okay, if we're looking at it from the instruction point of view, if we use this instruction right here, then odds are that the instruction after or the instruction before could be used in the future. So that's spatial. Temporal is strictly like, think of the machine learning or stock market. Temporal means if we use data in the past, we can probably use it again, so we better keep it handy. If we just ran an instruction in the past, regardless of where it is in memory or where it is in our program, there's a higher chance that we're going to use it again. So temporal locality is like your stock market. It's what you used in the past, you might use again. Spatial has to do with, if you're using something, let's look at the stuff around it. That's like me grabbing a bunch of files from the file cabinet, because odds are that I might use other files that are nearby the one that I'm working with. Okay? So I think that's enough time that I said that already. Hopefully you guys understand that. But if not, I highly encourage you to reread 4.1. It's very important. Okay? The principle of locality is another term for locality of reference, by the way. And the way that I put it in the book is, the principle reflects the observation that during the course of execution of a program, memory references by the processor for both instruction and data tend to cluster, which means they tend to group together. Programs typically contain a number of iterative loops and subroutines. Once a loop or subroutine is entered, there are repeated references to a small set of instructions. Similar operations on tables and arrays involve access to a cluster set of words or data words. Over a long period of time, the clustering use changes, but over a short period of time, the processor is primarily working on the fixed cluster memory references. So again, if we're looking at this, this might be a section of the array that we're sorting, which is going to be used a lot, but eventually that usage is going to kind of peak down and end, and then we're going to move on to the next section of the array. That usage is going to go very high and going back and forth here. So really what this will look like, I guess, will be like this. We're using this back and forth, back and forth, back and forth. Eventually we stop using that, and then they go to use that a lot, and eventually we use that as well. So that's going to be your spatial. And then your temporal is more, it's actually thinner for the temporal. They even do it in the book, because typically your loops are not 10,000 lines of code. Your loops are like 10, 15 lines of code at the top, if you're doing good programming techniques. Yeah, you can put it that way. Temporal is based on previous instructions, and spatial is based on physical. Yeah, so think about, physical. That's a good one as well. So anything that helps you to remember this is very useful. So that's locality of reference for you. And it's going to come in very important and key when we're trying to do branch prediction, because branch prediction can be kind of achieved using these two locality of reference principles, and also for caching, because caching is, again, that memory that is faster than main memory, and we have a limited amount of it, so we have to decide what we can store there. So if we just use something, we might use it in the future, so we might keep it in the cache, right? That's your temporal. Or if we're dealing with an array, and we don't know that we're dealing with an array, as the computer doesn't know, but it kind of, if we're dealing with a piece of data, if we're going to use the data around that, we might have to load that in the cache just in case that we do, because then we have it ready to go, right? So it'll come in important into that. So that's why I keep emphasizing that this is very important. Okay? So temporal, tendency of a program to refer in the nearest future those units of memory referenced in the recent past. Spatial, tendency of a program to refer units of memory whose addresses are near one another. Again, spatial stuff gets defeated by something like a linked list, but that's okay, because hopefully temporal takes over. So, and then they have the file cabinet example that I said that the book has. Any questions? And this clustering, by the way, I do mention in the book that happens on the web a lot. A lot of the times, think about Google's point of view, what Google should preload, in the cache and things like that. People seem to search the same thing over and over again. You don't search for an obscure phrase, and if you do, you're the only one searching for it. Other people don't search for it. So it's better for Google to have ready to go sort of generic results, trends, analyze trends. That's why they analyze trends, so they can have, information more ready to go and newer on those things. I bet you right now, a high trend of Googling is COVID-19. Everybody Googles that because they want to find out details. So Google's actively making sure that it has the latest search data for COVID-19 because of that. Nobody's going to Google about the Beatles right now. So that's going to be probably on the low end of things. So, yeah. How do computers identify that a function or a loop is temporal? They don't. They don't necessarily identify it. They don't really know, because in assembly it doesn't even look like a loop, right? It's just a jump with an if statement. So they don't. However, because of the temporal locality, they know that the code that just was used might be used in the future. And so if they start to see that code keeps getting used over and over again, they can sort of raise the priority of keeping this code in the cache, which is sort of the computer's way of detecting that it's a loop. But it's not something that it just directly knows. It's just kind of like, it's like if I just told you to do a bunch of things, but I didn't tell you that they were loops. After maybe doing it 5 times the same thing, you might realize that you're in a loop, right? You're stuck in a time loop or something. So, if a random person showed up on Twitch and started looking at my 202 live streams at like 5 p.m., they might, after the 4th time that I go live at the same time, they might start to pick up on the fact that I go live at the same time, right? But before they know that, they can just sort of guess that if I came up live at 5, I'm going to come alive again at 5. That kind of thing. So the computer doesn't necessarily know that it's a loop. It just picks up on these hints that things kept being used over and over again, and so it reinforces the idea that it really needs to keep this information in memory as long as it can. And by memory, I mean in cache, because that's the faster memory. So that's where we'll end it for the day. And for tomorrow, make sure you finish reading chapter 4. And yeah, I think that'll be enough. I don't even know if we'll finish chapter 4 tomorrow. So just make sure you read it, and we should be good. So cool. Anything else? Today we got to talk about interrupts and locality of reference. I'm happy. That's as far as I thought we would get. All right. Thanks for coming, guys. Yeah, make sure you at least wrote one message so that the attendance works on the script. So cool. Have a good day, everybody.